This is a continuation of chapter 14, which is on chemical kinetics. And I'm just going to finish going through the notes and work a few more problems for you. I realized after you left out of class today that I didn't actually finish the second half of sample exercise 14.7. I'm going to take a few minutes now and work through the rest of this problem. And just as a reminder, we are looking at this particular equation here. We had started out working the problem part A, looking at fertilizer that was polluting a lake. So we're going to continue looking at that example in part B. So in part B, this equation or this problem says, how long will it take for the insecticide concentration to decrease to 3.0 times 10 to the negative 7 grams per cubic centimeter? So in this example, we want to know how long something is going to take. So we're looking for time. That's what we're trying to solve for here. We have already previously in the problem been given K, and K was equal to 1.45 e to the negative 1. So we already have that. We already know our temperature is constant, so we don't have to worry about that. We are asked how long it's going to take to reach a certain concentration. So the concentration that they are giving us is going to be our concentration at a certain period of time, because that's the concentration that we're looking for. And they tell us that that is 3.0 times 10 to the negative 7 grams per cubic centimeter. And we already know from the information given to us that our initial concentration was 5.0 times 10 to the negative 7 grams per cubic centimeter. So we have 3 of the 4 pieces of information that we need. We have our initial concentration, we have our concentration at a particular point in time, we have K, our rate constant, and we're going to solve for T. So just as a reminder, this is our equation that we are working with here. Of our concentration at a certain time equals negative KT plus natural log of our initial concentration. So let's just start plugging this information in. I'm going to leave the T there because we're solving for T. Okay, so the first thing, I'm going to take the natural log of my concentration that we're trying to reach, and that is negative 15.02. That equals negative 1.45 T. And then I'm going to do my natural log of 5.0 times 10 to the negative 7. And that equals minus or negative 14.51. So now I need to isolate the T here because that's what I'm trying to solve for. So I'm going to add 14.51 to both sides. And once I do that, I get negative 0.51 equals negative 1.45 T. So now I'll divide both sides by negative 1.45. And when I solve, my time is going to be 0.35, and that unit is year. So how long is it going to take to reach a concentration of 3.0 times 10 to the negative 7? It's going to take 0.35, or about a third of a year, so somewhere around 4 months. Okay, so that is how we solve the second part of 14.7. Now, I want to draw your attention also to practice exercise 2. That's on that same page, page 588. In this one, they give us a decomposition reaction. They give us our rate constant, so they give us K, and they give us initial pressure, and that is 135 torr, and they want to know what is its pressure after 1420 seconds. Even though we're not dealing specifically with the concentration like we have here, we're dealing with pressure, we can use the exact same equation to solve this problem. So they have given us K, our rate constant, 6.8 times 10 to the negative 4, S to the negative 1, so we have K. They're giving us our initial pressure, so that would be like our concentration of A initial, which is 135 torr. They're giving us T, which is 1420 seconds, and they want to know the pressure at a certain time. So we have the K, the T, and our initial pressure, and we're solving for our pressure at a certain time. So we can use this exact same equation even if we're not specifically talking about concentration. Now, moving on from there, we get into second order reaction. So our next blank here is going to be second order reaction, is one where the rate is either going to have a reactant that's raised to the second power, a reactant concentration raised to the second power, or two reactions each raised to the first power. So, if we had an example that looks like this, we would add those exponents, and that would be a second order reaction. Or we could have one like we looked at in class today, where our reactant was raised to the second power. Both of those are examples of second order reactions. Our integrated rate law for a second order reaction looks a little bit different than it did for a first order reaction. If the reaction is second order, a plot of 1 over our concentration at a certain time versus time is going to yield a linear graph. So it's going to yield a linear or a straight line. So we talked about a first order reaction giving us a straight line. In a first order reaction, the graph of natural log versus time gives us a straight line. In second order reaction, we're not looking at natural log. We're looking at 1 over our concentration at a certain time. Gives us a straight line that has a slope of K and a y-intercept of 1 over our initial concentration. So we have to be careful here if we're plotting graphs, because we have to look at, are we plotting the natural log, or are we plotting 1 over our concentration? So that's what sample exercise 14.8 is going to look at. So sample exercise 14.8, it is on page 590, and it takes a look at determining our reaction order from the integrated rate law looking at data. So if you look on page 590 in your textbook, you'll see data. We have time, and we have our concentration of NO2, which is our decomposition of our reactant here, which is nitrogen dioxide. And the question says, is this reaction first or second order? Well, looking at the data that's been given, we can't easily determine this like we could in those examples we worked in class. So what we have to do is actually figure out the rest of our data and draw simple graphs and plot it to determine, is this a first order or is this a second order? So what we have to do is we're going to have to first figure out what is the natural log of our different concentrations of NO2. And then we're going to look at, okay, so then what are our concentration, or what are our plots if we look at 1 over NO2 concentration? So if this is linear, then it's a first order. And if this one is linear, then it's second order. Okay, so we're going to have to determine some points on our graph and draw it out. So the easiest way to do this is to take the data that's given for you in the book and then put a couple more columns on the table so that you can put your data in there. So that's what I'm going to do now. I've been given my time. All right. So there's my time, and I've been given my concentration. So let me go ahead and write those down. So there's the data I was given. So now I need to calculate my natural log of the concentration and put that in this column. And then I need to calculate 1 divided by my concentration and put that over here in this column. So I've done that, and I'm going to fill this in for you. So then I need to plot these. Now, in the essence of time, I'm going to just go with the graphs that are in the book. But basically, the way that you would do this, just kind of giving you an example, is you would just draw out a simple little graph here. Time is always going to go on the x-axis, okay? And what you're plotting, whether it's the natural log or the 1 over the concentration, that's going to go here. Okay, so what's dealing with your concentration goes here. And then you're going to plot 0 as your time here, your starting time, initial time, and then just make, some equal hash marks here. And plot those out. And then you're going to do the same thing for, and we'll just do this one here first. And try to keep your tick marks, close to the same. And we'll have, negative 4.6, negative 4.8, negative 5.0, so on and so on. And once you plot that first one, the natural log, it looks like this. Well, we can see that this is not linear. Okay, so it's not linear. And what did I say? Well, if the natural log is linear, then it's a first order. Well, that's not linear, so it's going to have to be a second order. So once we plot 1 over the concentration, we can see that this is linear. So this has to be a second order reaction. Okay, so for 14.8, it ends up, this is the one that is linear. So we have a second order reaction. Okay. Now, they may ask us, once we've done this, to determine what K is. What is our rate constant? Okay. And if we want to determine our rate constant, just remember our equation looks like this. So if we want to solve for K, K is going to be equal to the slope of our line. And we can easily use our equation to solve for this. So if we put in our equation for a second order reaction, it looks like this. And we can plug in any line up here on our data and solve for K. And when we do that, K is going to be equal to 0.54 meters, or molarity to the -1 second to -1. So just keep that in mind, that if they ask you to determine what order reaction it is, and then they come back and say, hey, give us the rate constant. Well, when you have that linear or that straight line, K in a second order reaction is equal to the slope of the line, we can just plug in some data, solve for K, and that gives us our rate constant. All right. Now, moving on a little bit further here, we get into our zero order reaction. So a zero order reaction is one in which the rate of disappearance of A is independent of the concentration of A. Okay, and you can see our rate law and our integrated rate law looks a little different from the others. We still have the same 4 components here, but now we don't have any fractions, we don't have any natural logs, and this is going to be an equation for a straight line with a vertical intercept of our initial concentration and slope negative KT. So the most common type of zero order reaction that we have is when a gas undergoes decomposition on the surface of a solid. And if we have a solid surface and that surface is completely covered by those decomposing gas molecules, the rate of reaction is constant because the number of reacting surface molecules is constant. So zero order reaction is one in which the rate of disappearance of A is independent of the concentration of A. Okay. Now, we talked about half-life last term in Flex 1 in University Chem 1, and the half-life of reaction is considered again here in this chapter because it deals with concentration, or we can use half-life as a measure of concentration. So the half-life is the time required of a reactant to reach half of its initial value. And it is a way that we can describe how fast a reaction is going to occur. We're only going to consider this for a first order reaction. And here is our condensed equation for this, where it's the negative log of 1/2, because we're trying to get to half, divided by our rate constant. And if we take the negative log or negative natural log of 1/2, that comes out to be 0.693. So half-life is equal to 0.693 divided by our rate constant. And as long as we know one of these two, if we know half-life or if we know the rate constant, we can calculate the other one. So let's look at sample exercise 14.9. And again, we're only going to look at these for first order reactions. It says the reaction of C4H9Cl with water is a first order reaction. Use figure 14.4 to estimate the half-life for this reaction, and then use the half-life to calculate the rate constant. So you have this figure in your notes, the one we've kind of referred back to several times. So our initial concentration is 0.1. So half of that would be 0.05. So we need to determine the time from our graph here, from our line, the time we reach 0.05 for our concentration. And so that's going to be right about here. And if we kind of follow that down, we're not quite at 350. Your book calls it 340, so that's what we'll go with. But again, just like when we talked about drawing tangent lines, if you get close, then that's good enough for me. So we're going to say that our half-life is about 340 seconds. And we just took that from the graph that was given to us. So now we know our half-life, and they want us to figure out K. So our half-life times K is equal to 0.693. And so if we divide both sides by our half-life, that will give us K. So K is going to be equal to 0.693 divided by 340 seconds. And when we do that math, we come up with 2.0 times 10 to the negative 3 s the negative 1. So this is our rate constant for that particular reaction. So again, if we know either half-life or our rate constant, we can solve for the other one. The next section gets into temperature and rate. So remember that temperature is one of the factors that can influence reaction rate. So the rates of most chemical equations, as we've already mentioned, are going to increase as the temperature rises. And this faster rate is due to an increase in the rate constant. Remember, the rate constant is affected by increasing temperature. So the reaction rates here are affected by both reactant concentration, as we talked about, and temperature. And this all goes back to what we've kind of been talking about this whole time, the collision model. The greater the number of collisions per second, the greater or the higher the reaction rate. So as we increase reactant concentration, or as we increase the temperature, we are going to increase the number of collisions that are occurring. Now, with increase in temperature, we're increasing the kinetic energy. So when those molecules collide, they are going to collide more forcefully because they have more energy, and more frequently because the concentration is higher. But remember that just having the molecules collide is not enough to cause a reaction to happen. It has to be the right kind of collision. So it can't just be a collision, it has to be the right kind. We have to have the right molecules in the right orientation for a reaction to occur. So let's talk a little bit about this orientation. So in most reactions, the collisions between the molecules are going to result in a chemical reaction only if they are oriented in a certain way when they collide. So if they have a lot of energy and if we have a lot of collisions, it doesn't necessarily mean that we're going to have a chemical reaction. They still have to be turned in the right direction. And so in most reactions, it takes thousands of collisions, but we only end up with a fraction of those being able to cause a reaction. The relative orientations of the molecules during that collision event determine whether or not the molecules can form new bonds. So when these molecules collide, we may have to have breaking of bonds, and then we're certainly going to have the creation of new bonds. So in 1888, Svante Arrhenius, who was a Swedish chemist, came up with this idea that molecules have to possess a certain minimum amount of energy to react when they collide. And once they collide, the energy of these molecules, and specifically the kinetic energy, which remember is energy of motion, is what leads to the chemical reactions. So if they're moving too slowly, so they don't have enough energy, then they're just basically going to bounce off one another, just like you bounce a ball off a wall. Okay. The minimum energy required to initiate a chemical reaction is called the activation energy. And that is, and I just realized I didn't correct that one. It's E sub A. That is your activation energy, E sub A. This one I wrote incorrect. This is the correct one here. Activation energy is going to vary from reaction to reaction. And the reaction rate depends on the magnitude of activation energy. The lower the value of activation energy, the faster the reaction. We can think of activation energy as like a hill that we have to climb in order for a reaction to occur. And your book gives the example of a golfer, and they're trying to put the golf ball into the hole. And right get over the hill to make it into. I accidentally keep pausing my recording, sorry. The ball has to get over that little hill. And so that's like a barrier. And the activation energy is the barrier between our initial and final state. So it's like this hill. And so your question says, if the barrier were lower than what's shown in the figure, would the golfer have to hit the ball as hard? No, he wouldn't, because it's a smaller barrier. So the smaller the barrier, or in our case with activation energy, the lower the activation energy, the faster the reaction. So Arrhenius, he did a lot of work with activation energy and reactions, and he came up with an equation. And what he said is that most of the data around reaction rate obeyed a particular equation based on three things: the fraction of molecules possessing a particular amount of activation energy or higher, the number of collisions per second, and the fraction of collisions that have the appropriate orientation. And so once he kind of figured that all out, he came up with his own equation, where we have K as our rate constant is equal to A, which is the frequency factor. This is a constant based on the particular molecules that we're talking about. And this is how frequent the collisions are, okay? And then E, remember E is the reverse of the natural log. And so that's going to be raised to the negative activation energy divided by the gas constant and the absolute temperature. Now, the absolute temperature is our temperature in Kelvin. And just as a reminder, we take our degrees Celsius, add 273.15, and that gives us our absolute temperature in Kelvin. So this is called the Arrhenius equation. Now we can manipulate this to calculate the activation energy for a reaction by taking the natural log of both sides. Because again, remember, this is the inverse of the natural log. So to get it out of that form, we take the natural log of both sides. And we can calculate the activation energy by measuring K at a series of temperatures, graphing the natural log of K versus 1 over T, because T is on the bottom here, and then calculating EA from the slope. Okay. We can also manipulate our equation a little bit more to evaluate our activation energy in a non-graphical way. So in other words, without graphing, if we know the rate constant, K, of the reaction at 2 or more temperatures. And so we just take the natural log here of our rate constants at 2 different temperatures and then input those temperatures here. So this equation, the Arrhenius equation, is basically going to allow us to calculate activation energy. And I gave you a cheat sheet on this where it goes step by step on how to calculate the activation energy for a particular reaction. This is something that you're going to do with the labs that you're going to work on. Now we're going to look at sample exercise 14.11 on page 598, where we can look at data given to us and determine our activation energy. So first thing we've got temperature and we've got K. We've got our rate constant given to us. And it says, from these data, calculate the activation energy for the reaction, and then what is the value of the rate constant at 430.0 K? So it's a two-part question. So we're given the rate constant at 4 different temperatures, and then asked to determine, for part A, the activation energy. So remember, we can determine activation energy by looking at a graph and calculating the slope. So that graph is natural log of K versus 1 over T. So just like we did before, we're going to kind of extend out our table to put this other information in. So the first thing I'm going to do is just kind of draw out what's here. But remember, we're talking about absolute temperature. So we need to convert our temperature to Kelvin. Okay, so that's going to be one of the steps that we're going to have to do. They've given K, and that is in S to the -1. And then we're going to have to take the natural log of K and 1 over T, which will be the units K to the -1. So let me go ahead and write in what was given to us. I probably should have made that box a little bit bigger. And we can see as the temperature increases, our rate constant gets smaller. So the first thing we need to do is get our temperature in Kelvin. So again, I'm going to take this and add 273.15 to each of these and still keep with 4 sig figs. So here's what we're going to have. So there's our temperature in Kelvin. So now I'm going to get my calculations so that I can get my graph and determine what my activation energy is going to be. So let's write in this data. And really, you don't have to keep a table like this, but it does make it handy, especially when you have to do the graphs, because it's all right there in one place. All right, so now I have done all of my math here that I need to do, gotten all of the information that I need. So we did our natural log of our rate constant, we did 1 over temperature, and the graph of these is a straight line. So when we're looking at activation energy and we graph this, we're going to be looking at a straight line. So let's look in your book, because I've already got that done. No use in me trying to do a worse version of it. So there's the graph. We put the natural log of K on the y-axis. We put 1 over temperature on the x-axis. We plot our points, and we draw our line. And we have to determine now this slope of this line so that then we can calculate our activation energy. Okay, so what we do to calculate slope, and if you remember this maybe from algebra, that slope is equal to rise over run. Or if we get a little bit more technical, the change in y, so delta y over the change in x, which is delta x. And you just have to pick some points. It doesn't matter what points you pick along the way. You just have to pick some points in your linear graph here and calculate the slope. The big thing that you want to do is make sure that the points are well separated. So with how they did this in the book, they picked this point right here and this point right here. Okay, and so that's what we're going to go with in the interest of time. So negative 6.6 minus negative 10.4. So those were their two points that they picked along the y-axis, and this is, y2 minus y1 over x2 minus x1. Is that right? Maybe y1 minus y2. As long as you do them the same. I honestly can't remember now that I'm saying it. I've gotten all mixed up in my head. But take the one y point minus the second y point, and then we're going to do the same thing for our x-axis, 0.00195 minus 0.00215. And that gives us negative 1.9 times 10 to the 4. So that is our slope. Okay, so the slope of that line that we drew is negative 1.9 times 10 to the 4. Now, the unit for slope is K, because natural log is dimensionless. We're looking at temperature, and so our unit on our slope is going to be K for Kelvin. Okay, so negative 1.9 times 10 to the 4 Kelvin. Now, slope is equal to negative EA, which is our activation energy, divided by R, which is our gas constant. So if we multiply to get the activation energy by itself, we'll say slope times R is equal to negative EA. We can just reverse that sign. So negative slope times R, our gas constant, is going to give us our activation energy. So we're just going to plug in. We got our slope. Okay. And our gas constant. Okay. So our units of Kelvin are going to cancel out. Our negative times a negative, we're going to end up with a positive. You should always end up with a positive number for your activation energy. And so we're going to get this, and then we're going to convert it into kilojoules, because remember, joule is such a tiny, tiny amount that we're going to convert that into kilojoules. So let me add my conversion on here for joules so that we end up with kilojoules per mole. And the answer that we get is 1.6 times 10 to the 2 kilojoule per mole, or 160 kilojoule per mole. So that is the activation energy. So this reaction that we're talking about right here, which is the rearrangement of methyl isonitrile. In order for this reaction to occur, we have to put in 160 kilojoules of energy per mole of methyl isonitrile. That's what that means. If we don't have at least 160 kilojoules of energy, then that reaction will not occur. Okay, so that is part A. We have solved for our activation energy. But there was another part to this problem, and it said, what is the value of the rate constant at 430.0 Kelvin? So we want to know the rate constant at 430.0 Kelvin. So we're going to use our equation here. We're going to use this equation right here because we're going to use the temperature that they gave us and a temperature that we already know. We've calculated the EA, we've got a rate constant. So we'll be able to figure our rate constant at a particular temperature using that equation. Okay. So we're going to say we've calculated our activation energy, so we know what that is. And we're going to use one of our rate constants here. So we'll just use this first line. Remember, we can use any line that we want to, but we're just going to use that very first line there. And so we're going to say that K2 is equal to 2.52 times 10 to the negative 5 S to the negative 1. And I got that from right here. And we're going to use that temperature. So that's going to be Q2. If that's K2, then we have to let our temperature there, 462.9 Kelvin, be our T2. We know, here's the temperature they asked us. We're going to set that to be T1. So then we plug into our equation, and it's going to look like this. There's my activation energy and my constant R. And then I'm going to plug in my temperatures. There. Okay. And then, because I converted this to kilojoules, I got to go back to joules. So I need to include that in my reaction as well, or in my equation, sorry. Okay, so let's put it in there. And so now we can kind of get some things that are going to cancel out, and we can rearrange. And so this second part here equals negative 3.18 because our kilojoules cancel, joules cancel, my mole cancels, and then my Kelvin cancel. And you think, well, wait a minute, you've got two, but when we subtract this, we only have one, right? And so that Kelvin will also cancel. So our answer here on this side of the equation is negative 3.18. So now we have to get rid of that natural log, right? And remember, to get rid of that natural log, we use the inverse log. So this is going to equal E to the negative 3.18 power, which equals 4.15 times 10 to the negative 2. But we're not done yet because we've gotten rid of the natural log now because we've used the inverse of that. But we have to still figure out our K1. So I've kind of run out of room. Let me grab another sheet of paper here that I can work. So we are K1 over 2.52 times 10 to the negative 5 S to the negative 1 is equal to 4.15 times 10 to the negative 2. That's where we are because we've completely solved this half of the equation. We've taken the natural log, the inverse of the natural log of both sides. So that got rid of our natural log. So here's where we are now. We can set this up just like a fraction. That would be the same as saying, over 1. And when we cross multiply, then K1 is going to be equal to 4.15 times 10 to the negative 2 times 2.52 times 10 to the negative 5. Okay, and when we do that math, we get 1.0 times 10 to the negative 6, and our unit, because we only have one unit, is s to the negative 1. Okay, so that was kind of a lot of running out of room there, but once we have activation energy, we can calculate reaction rate at any temperature we want to. Or they could have given us a second reaction rate constant there and asked us to determine temperature. So again, this is just like all of the other reactions we've been looking at. If we have these factors here, if we have, our reaction rate, we have our temperature, we know R, we can calculate that, our activation energy, or we can manipulate this to solve for any of these things if we have the others. Okay, so it's just a matter of taking your time to plan this out so that you think about what you need to use and what each particular data point that you're given means. Okay, so it's just a matter of figuring out, okay, what are each of these? What am I solving for? How do I set up the problem? Okay, because once you get your problem set up, then it's just a matter of plugging and chugging, right? And again, just remember to take the inverse of the natural log. We use that E caret button, okay? And that's what's going to get us out of that natural log. So that takes us through section 14.5, and I've gotten long-winded again. So I'm going to stop now and then record a much shorter video on sections 14.6